Now we move into the next phase, how atomic theory evolved with new discoveries. Dalton's model saw atoms as these solid, indivisible spheres, but by the late 1800s, scientists started asking some deeper questions. Could atoms have internal parts? Could they carry a charge? And are they truly indivisible? This curiosity led to a series of experiments that revealed atoms are made of even smaller particles called electrons, protons, and neutrons. And this began with J.J. Thomson's cathode ray tube experiments, and it continued with what's called an oil drop and gold foil experiment. And each one of these experiments, they added a new layer of understanding and changed our model of the atom today. So Dalton really wanted to know what atoms were composed of and if there was really anything smaller than an atom itself. So J.J. Thomson experimented with cathode ray tubes. And this is a sealed glass tube where all of the air has been removed from the tube. And it has these two metal electrodes on each side. And what he did was he applied an electrical charge or high voltage between these two electrodes, and it caused a beam of electricity to be seen. That you could see the the charges between them. And it didn't matter what type of metal was used. The beam was always deflected toward the positive charge and away from the negative charge. So Thomson was able to calculate the charge to mass ratio of these cathode particles. And what he found was that these ray particles were lighter than atoms and that they were also negatively charged. Essentially, he found electrons. He discovered that electrons are negatively charged and that they have a significantly smaller mass than protons and neutrons. So they're very much lighter than atoms themselves. So he didn't really find the protons and neutrons yet. I shouldn't have said protons and neutrons. Really, he just found that they were lighter than the atoms themselves. But this is what the cathode ray tube looks like. So he had high voltage here on the left side, and there's something called a cathode that's a negative charge, and an anode is positively charged. And then he has a battery connected to that with some of these charged plates between them. And we could see the beam in the cathode ray tube. Robert Millikan, he also was a contributor to the scientific discovery of the different parts within atoms. He created these microscopic oil droplets. He was able to spray oil, which were electrically charged, in order to make some calculations about their charges. And he found that these drops could be slowed or reversed by electric fields. He was able to determine the charge on these individual drops, and he was able to measure them using this device. So he would spray these oil droplets through this very small opening here, and they would land on this plate, and essentially the plate is positively charged, and then below it is negatively charged. And he was able to measure the overall charge of these different oil droplets. And then he was able to also look inside as this was occurring while these were electrically charged. And he tabulated the data below. He ended up just averaging out what this data was to find the total charge in coulombs. And Thomson had already showed the charge to mass ratio of an electron to be 1.759 times 10 to the 11 coulombs per kilogram. And Millikan found out that these drops were always in a multiple of 1.6 times 10 to the negative 19 coulombs for their charges. So he concluded that this was the charge of an electron. So since Thomson had found the charge to mass ratio of an electron, that now we're able to calculate the mass of an electron. So Millikan found the charges, Thomson found the charge to mass ratio. And so now we can find the mass of an electron using just a simple conversion here. So there's 1.759 times 10 to the 11 coulombs per kilogram for electrons, and we can write that in the other direction. We can say 1 kilogram to 1.759 times 10 to the 11 coulombs. It's a ratio, so it can be written either way. And so now we can cross out coulombs and coulombs, and we're left with 9.107 times 10 to the negative 31 kilograms. And that's the mass of an electron. J.J. Thomson also suggested that atoms are what he referred to as in a plum pudding model. So at the time, plum pudding was a common food for people to eat, and it basically is just cake with plums inside the cake. And he said that it's very similar, an atom is very similar to plum pudding. So he thought that there were electrons that were inside of this positively charged pudding, where the electrons would be considered the plums, and then this would be the pudding here. So he thought that that's what an atom looked like. Nagaoka was another scientist who proposed that atoms they resembled the planet Saturn, with a ring of electrons surrounding a positive planet. And so this is much closer to the model that we accept today, although it's still a little bit different than what we see today. So the electrons don't exactly orbit in this nice pattern of an orbit. Sometimes we show that in diagrams, but we're going to learn later in this course how electrons travel in these paths called orbitals. Another scientist who contributed to the scientific discovery of the components of atoms is Ernest Rutherford. And he had what's called a gold foil scattering experiment. So what he did is he was able to get these alpha particles and concentrate them toward a very thin piece of gold foil. And alpha particles, we're going to learn more about alpha, beta, and gamma particles when we go to nuclear chemistry. But alpha particles are positively charged particles, and when they become scattered through this screen, they would glow when they hit something. And here's a diagram of what that looks like. So these alpha particles would be directed in a single beam, and this is very thin gold foil. You could almost maybe even see through it. It's a very thin sheet of gold foil. So these alpha particles, they're directed at the gold foil, and theoretically, we might think that, well, if it's gonna either go through the foil or it's gonna bounce back. But it did something a little bit interesting. Some of them went straight through the foil, but some of them were dispersed or deflected in these different angular directions. Some of them were almost directed all the way back to the source, so they would bounce back over in this direction here. So it was kind of interesting to see how there were some major differences in the direction of these particles. So let's think about what happened in his results then. He he determined that an atom has to be a lot of empty space then, um, because this foil, even though it was thin, we were still able to move particles through it. So he was thinking that, well, if it went through, then it must have had to be empty space. So there's a small, heavy, positively charged body called the nucleus that must be at the center. That's what he had discovered from this. That the nucleus contains most of the atom's mass and that negatively charged electrons are surrounding that nucleus. And also that the proton is positively charged and it's also located inside of the nucleus. So here's a more close-up look of what was happening here. So here's the beam of particles. They're all going this direction. And what's happening is the nucleus is very small, and sometimes the particles are coming into contact with the nucleus. Other times they are not. They're just going through they're going through the atom, but there's empty space there. So it's just moving through the atom. Here they're moving between the atoms. Here they're coming into contact with the nucleus and they're bouncing back at a different angle. And some of these, they just graze the nucleus, just barely graze the nucleus, and then it gets slightly deflected to one side. All right, some other important discoveries that we found from the 20th century are isotopes. These are atoms of the same element that have a different mass. Frederick Soddy of England, he won the Nobel Prize in 1921 for discovering this. Also, neutrons, they're uncharged subatomic particles. They do have a mass, and that mass is equivalent to the mass of a proton. So neutrons are found in the nucleus as well. So the nucleus is a collection of protons and neutrons, and then the electrons, they have the opposite charge of a proton, and they help to hold together the nucleus, and everything is in this balance between the different parts of the atom. All right, and here's the associated practice assignments with this part of the lesson.